Page 116, question 20. Okay, they say there, 20.1. An electrochemical cell is set up using aluminium and a gas, aluminium solid. Yes? Ai, toch. Okay. And so aluminium solid and then gas X. So X, that is a gas. Okay. Now they say the initial EMF measured under standard conditions. So the EMF of the cell under standard conditions is 2.89 volts. Okay, now they ask, state the standard conditions under which the cell operates. Standard conditions under which it operates. Jabu. I like to start with you. Because you always take a few minutes to get ready, so I'm just helping you. That's how it works, ne? So it's either you or Maritava that's going to answer this question, because this was Mama's question the previous lesson. What is standard conditions? The concentration, so let's say the concentration of the solution. Was it yours? Well, okay, 1 mole per decimeter cubed, and what's the other one? Yes. And that is of the solution. Okay, so not the air around us, the solution. Now they asked the 20.1.2. Use a calculation to identify gas X. Okay, it counts 5 marks. So they've already given us the volts of the cell. We know the one is aluminium. So if we do this calculation, E of the cell is E cathode minus E anode, then we can get which one is the gas. Yes? But the problem now is, what is aluminium? Is aluminium at the anode or at the cathode? Which one is it? Okay, where are we going to go to assist us? For B. Oei, en ek is by 'n heel verkeerde hoofstuk. Hier het grade 10 work. Okay, table 4B, where are we? Okay, so we know we have aluminium. Okay, there's aluminium, that's the one. Okay, so we want to know, does the Z go like this somewhere there, or does it go like this somewhere there? Okay, like what is aluminium? Is it the oxidation half reaction, or is it the reduction half reaction? Now, look at the top of aluminium. Do you see any gases here at the top? No. And they told us specifically it is a gas. So it means whatever the gas is, we don't know what it is, it must be below aluminium. So aluminium must go this way so that whatever we have at the bottom goes that way. So aluminium must be the oxidation half reaction. And where does that take place? At the anode. Okay, so aluminium is the anode. So whatever this is the cathode. Okay, so they tell us the volts of the cell is 2.89. The cathode is X, we don't know what it is. And the anode, aluminium, if you check on table 4B, it is minus 1.66. Maritaba, when you are ready. Maritaba, what does that mean, Maritaba? Means what? Really? Is it true for your name? I believe your name, the meaning is true in your life. Like my name means free. And I do believe I am free. Jabu's name means joy. Joy brings happiness. Tawana, what does it mean? Oh, really? And are you fruitful? You must say, yes, ma'am, I am. Anyway, okay, off topic. Yes, Maritava. 1.23. And the unit? V for volts. Okay, but the question wasn't calculate. The question was, what gas is this? Okay, now we have to go check 1.23, 1.23. Now, if you check that, there are two 1.23s. This one and this one. Okay, let's check. This one has manganese dioxide in it. Princess, is this a gas? What is this? You should know. We did it this year, last year. What does it look like? Yes, manganese dioxide. It's a black powder. It's a very fine contact powder. We used it last year and I put in a glowing splint and it burnt again. Okay, so manganese dioxide, definitely not a gas. Okay, whereas here you see we have oxygen gas. So then the gas that we start with is then oxygen. Okay, then question 20.1.3, they ask, write down the formula of the reducing agent in the cell. The reducing agent. Okay, back to table 4b. So we have the, I'm going to use a different color now. So we started with aluminium, goes that way, and then we have oxygen there, goes this way. So there's our Z. Okay, and we said that at the top, that is the oxidation half reaction. So, Princess, because you didn't answer correctly, aluminium, is it the oxidizing agent or the reducing agent? Reducing agent, because it's the oxidation half reaction. So they ask for the formula of the reducing agent. So then you'll just say Al. Okay, 20.1.4 they ask, write down the half reaction that takes place at the cathode. Okay, so again, oxidation takes place at the anode. Reduction takes place at the cathode. So you are just going to go copy this formula, this equation exactly like it is on table 4b. You don't have to remove anything or add anything like that. So you're going to say oxygen gas plus 4 hydrogen ions. What does that hydrogen ion stand for? What does it mean? It means that this whole thing is in an acidic solution. It happens in an acidic solution, so we say it's acidified. Okay, and as you can see on table 4b, these arrows point both ways, but we just take it one way because we say this is the reduction half reaction. Okay, and then 20.1.5, thus write down the cell notation for this cell. Cell notation for this cell. Cell notation. Anyone want to give it a try for 2 sweeties? The cell notation. If you get it half right, you get 1, sweetie. Are you looking at me like you want to give it a try? Yes, Jabu. Okay, let's see. Always with oxidation.
Oxidation, and then it's aluminium, giving you aluminium triple. No, ma'am.
Yeah?
Can I do it first?
Yeah? You want to try? Yeah.
Yes, then it's going to be hydrogen ion, like the salt
Okay, yeah. And then?
hydrogen ion.
Do we start with...
Sorry, ma'am, oxygen is not oxygen. Hydrogen ion.
Hydrogen ion. Does it go to hydrogen ion?
Oh no, ma'am, water, sorry, water.
And what do they say there the water is? They don't say what it is, so I want to say liquid. Okay. Yes. There's something missing. Something is missing. Wait up. Is al die stoute kabouters hier vandag in julle klas? So you guys are going to have a rustige day. What? Not a rustige day. You can make it enjoyable. That doesn't even make sense in my head. Okay, well, anyway, let's not. I'm recording everything. Let's not have a discussion on that. Yes, Jabu. Okay, no wait. You did the net cell reaction. That's not what we want. We want the cell notation. Cell notation is the name of the cell. So you start with the oxidation half reaction this side. So aluminium went to aluminium ion. Aluminium is a solid, so it can be its own electrode. Then you have a salt bridge. Then you look on table 4b. What went to what? It's the oxygen. You can ignore that hydrogen completely. Oxygen went to water. Okay, so you write that down. Oxygen gas went to water, but water is not a solid. Water is a liquid. It's floating around there at 25 degrees Celsius. Okay, so we need another electrode there, and the electrode that we have or use most often is platinum. So if one of these things at the side is not a solid, then you make another line and you write platinum. PT for platinum. So I'm going to say this. This is a solid, so it doesn't need a platinum. If this was liquid, then you would have written platinum here. Okay, but since it's a solid, no platinum. But this here is a liquid, or if it is a gas or whatever, something that is not a solid, then you write line platinum. Okay. Then they'll ask a question 20.2. Which container, a zinc or a copper container, will be more suitable to store an aqueous solution of nickel ions? Use this table of standard reduction potentials to explain your answer. Okay, so we must go to table 4b. Okay, I'm going to get a clean table 4b for myself. Okay, so they speak about zinc, they speak about copper, use this copper, and then they say for nickel ions. Okay, and they ask which one will be more suitable to store these nickel ions in them. Okay, now, if we have a container, if I have this liquid here, okay, this is copper chloride actually, but I have this, let's say this is nickel ions. Do I want the nickel ions after a while to form a precipitate, to form a layer of nickel around it here? No, because I want the liquid to do whatever with it. So I do not want the nickel to go to nickel ions, nickel solids. I do not want it to be reduced. Okay, now which one, zinc or copper, will cause nickel to be reduced? Look at your Z. For a sweetie. Okay, why do you say zinc? True. Okay, of the what? Okay, you must say which one is stronger or which one is weaker. So you can't just say it's decreasing. Okay, so she says, ma'am, if we look at this Z here, if we look at those two, zinc and nickel ions, then nickel ions will be reduced. It will gain electrons to form nickel solid, and we don't want that. So that is why zinc is not a good option. We would rather want the reaction to go this way, because the copper would not want to go into copper ions, and the zinc would not want to form nickel would not like to form nickel solids. So it's better to put it in a copper container. Okay? But you can either look at the strength of the reducing agents or oxidizing agents. Okay? So Tawana chose to look at the oxidizing agent. So she will say nickel is a weaker oxidizing agent than copper ions, or copper ions is a stronger oxidizing agent than nickel. Okay? Or she can say zinc is weaker than nickel or whatever. Okay, so you compare the two things with one another. Okay, so I'm going to write there 20.2. Let me just get to my paper. I'm going to say nickel ion is a weaker than copper 2 plus ions. Thus, nickel ions won't be reduced when okay, so I'm going to explain again what I wrote down there. So I looked at nickel ions and copper ions. I looked at the left-hand side, and I said, okay, so because nickel is higher up, it's a weaker oxidizing agent. What does it mean? That it won't be reduced. Or you could have said it the other way around. You could have said copper ions is a stronger oxidizing agent than nickel. So copper would rather be reduced than nickel. Okay? But they say we must compare it with zinc as well. So I'm not going to just stop there, because I think this counts 4 marks. So you must mention more. Now I'm going to compare nickel with zinc. So I'm going to say zinc ions is a stronger oxidizing agent than zinc ions. Okay, so I'm going to explain again what I wrote. I looked at nickel and zinc. Where are they? Nickel and zinc. And I saw that nickel is lower down, so it's a stronger oxidizing agent than zinc. So if this was placed in a zinc container, then the nickel will be reduced to nickel solid. Okay, which is not favorable. Let's just answer the question. They ask, what was the question they asked? Which container will be more suitable? So we must say, thus copper more suitable. Okay, let's go to question page 125. Question 17. Okay, they say there, the simplified diagram below represents an electrochemical cell. Okay, so you can see there we have a direct current source, so it could be a battery or whatever, it doesn't matter. With an electrode, and then we have something there. Okay, and they just say there is impure copper. Okay, now they ask, or they say there, the simplified diagram, the impure copper contains small amount of silver and zinc as the only impurities. So we have copper, silver, and zinc on there. Now they ask, define the term electrolysis. Electrolysis. Wat trek ons met die vraag? Ja, wat is dit wat? Sê ja. Mhm.
Or the use of electrical energy to produce a chemical.
Okay. So the process where electrical energy is converted into chemical energy. Okay. Okay, so now they want, they say there's impure copper here, but there's also a bit of silver and zinc, and they want to purify that copper, meaning they want it to deposit on there copper. Yes? Okay. Now they ask, name or formula of two positive ions in the electrode. Okay, now first, let's see what will make sense to be in the electrode. What must we make the electrode? Tawana. Yeah. What must be in this electrode? What must it be made of? Copper, because we want to purify copper. Okay, we want it to be copper, and then nitrate most probably, because nitrate is always soluble. Okay, so what will definitely be the positive ion in that electrode? It will be electrolyte, copper ions. Okay, what else? There might be silver ions in there, and there might be zinc ions in there, because they tell us there is silver and zinc also. Okay. Right. Then question 17.3. Write down the half reaction that takes place at the cathode. At the cathode. Cathode is again reduction or oxidation? Reduction. So reduction is at the cathode, and that is reduction is the gain of electrons or in electrons. Okay, so what do we want to happen? We want the copper to form a precipitate there. Yes? So we want the copper ions to gain 2 electrons and to form a copper precipitate, solid. Okay, I just want to check something quickly because I'm feeling that I missed something. What is this? Okay, yeah, I haven't missed anything yet. Okay. Okay, let's read the next question. Now they ask 17.4. Refer to the table of standard reduction potentials and explain why purified copper will not contain any zinc. So what they're basically asking is, of this impure copper, why will copper go into solution and silver will go into solution, but this zinc would not like to go into solution? That's what they're asking. Okay, so let's look. There's zinc, there's copper. Where do we have silver? At the bottom. Okay. So let's see if we compare a zinc with copper. Then this will go that way, and this will go that way. Okay, wacht. Is that the question that they ask? Explain why the purified copper... Wait, sorry. They ask why. So this is the impure one. They ask why will they not form any copper? That's what they're asking. Okay, so why will, even if... Sorry, this silver ions will go in here, zinc ions will go in here, copper ions will go in here, but they want to know why will the copper go form a precipitate there, but not the zinc. Okay, so again, table 4b. So if we compare zinc with copper, and this is the Z, then zinc is the stronger reducing agent, meaning zinc will just go into solution, but zinc will not form a solid because the arrow is pointing in that way. It's not pointing in that way. Whereas if you look here, copper ion is a stronger oxidizing agent, meaning it would form a precipitate the whole time. So if you compare the two things to one another, you can either say zinc is a stronger reducing agent, or you can say copper ion is a stronger oxidizing agent. Are you with me? Okay, so we can choose. Let's say we go to reducing agents because they don't say which one. So we're going to say copper is a stronger, and I'm going to abbreviate, please don't do that in exam. Copper is a stronger reducing agent than zinc. Thus copper will only oxidize to copper ions and not reduce from copper ions to copper. Okay. We don't have to mention anything from silver because they only say why will the purified copper not contain zinc? So they don't ask anything regarding silver. Then 17.5 they ask, calculate the maximum mass of copper formed if 0.6 moles of electrons are transferred. Okay. So they say the mole of the electrons are 0.6 moles. And they want to know what's the mass of specifically copper that will form. Okay, let's look at this copper half reaction. It goes from copper ions, it gains 2 electrons, and then it forms copper. Okay, so we see from here, if 2 moles of electrons gives us 1 mole of copper, that's a mole ratio, 2 mole of electrons gives 1 copper. Okay, so how many moles of electrons did we have? We have 0.6 moles. So if this is 0.6, then how many moles of copper? 0.3. Okay, this is moles of copper. Okay, but that was not the question. The question was the mass. So we have mole is mass over molar mass. The mole is 0.3. We want the mass. And the molar mass of copper is, I think, 63.5. $19.05 grams. Okay, so this question seemed, when we read it, we were like, what in this world? Okay, but it's not difficult. Okay, what you got to mark for here is for just substituting that in the correct place, because it counts 3 marks. Substituting that in the correct place, somewhere just write down that in your formula. And then knowing the mole ratio, and then your answer. Okay, I want to do another calculation like that. If we look at question 18. Okay, I'm not going to do the whole question 18 now. Okay, they just say this is a ring and chrome metal and the chrome ion, and they ask which one is the anode, which one is the cathode, write down the half reaction that takes place there, and then they ask, calculate the total charge transferred when the mass of pure chrome changes by 2 grams. Changes by 2 grams. So this is 18.4. Okay, wait, I'm going to give you 30 seconds to just start writing down a formula or an equation. Do something that you think can help you start. So maybe start with a half reaction. Okay. That was 60 seconds. What I wanted you to start with is writing down that and that. That at least you know you must look at the mole ratio and the number of electrons. And they speak about the mass, so you think maybe I should go to mole. So chrome gains 3 electrons to go into chrome solid. We don't know what's the mole. Why do we go to mole? Because then we can compare things to one another. You can't compare masses or volumes. Moles we can. They say the mass changes by 2 grams. So it gains 2 grams. And the molar mass of chrome is 52. 0.0385. Okay, so that is the mole of what? That is mole, of chrome. So this mole ratio is 3 to 1. The mole of chrome that we gained was so much. So to get the number of electrons that we gained, we must multiply by 3. So that gives you 0.115. Okay, what was the question again? Calculate the total charge. So we have a formula for charge. Charge is current times time. Times time, yeah. We also have that the number of charge, now that's not mole, that's the number of charge, is charge divided by the charge of an electron. Okay, now those are both formulas that are on your physics data sheet, not your chemistry data sheet. Now this question was asked in November 2021. I think they would have put these formulas on the data sheet, but I don't know. Okay. The one that you're going to use is this one. Because we know what's the charge of an electron that's on your data sheet. If we can just go calculate how many electrons, then we can calculate the charge. Now here we have the mole of electrons. How can we go to how many electrons? Now for that you have to go back into your grade 10 mind. I don't know if you remember this formula. Where the mole is this, number of whatever, electrons, ions, blah, blah, blah. And then this is Avogadro's number. Okay, so that's how many electrons, and then to get the charge, you're going to say that number times the charge of 1 electron. 6 times, also on your data sheet. And you get 1113.85 coulomb. Okay, difficult one, that's why I wanted to do it.